Chapter 16, Permutation Tests. Section 16.1, When and Why to Use Permutation Testing. Permutation testing is an empirical, computational approach to computing a p-value to evaluate the statistical significance of a characteristic of a sample. As you will learn in this chapter, permutation testing involves creating an empirical null hypothesis distribution using sample data, instead of deriving a null hypothesis probability function from a mathematical formula. This paragraph references figure 16.1, which shows a comparison of analytical versus empirical null hypothesis distributions. We see a histogram where the x-axis is just listed as value, with ranges from -4 to +4, and the y-axis depicts density in arbitrary units. We see a black line corresponding to the analytical probability function, looks like a Gaussian, and then we see gray bars, which correspond to an empirical null hypothesis distribution, also looks like an approximation to a Gaussian. Back to the text. From looking at figure 16.1, you may wonder why anyone would use a jagged and imprecise empirical null hypothesis distribution when they could use a mathematically defined analytical distribution. There are two situations when you would use permutation testing instead of parametric statistics. Situation 1. Your data violate assumptions of parametric statistics. Perhaps you have outliers, small sample sizes, a non-normal distribution, or other data characteristics that prevent a clean interpretation of parametric statistical results. Permutation testing involves creating an empirical null hypothesis distribution based on your sample data, so any unusual or assumption-violating characteristics of the data are incorporated into the null hypothesis distribution. Situation 2. You are performing an analysis with no known analytical H0 distribution. Although many analyses in the traditional statistics corpus have mathematically defined null hypothesis PDFs, many modern analyses have no known null hypothesis distribution. For these analyses, an empirical null hypothesis distribution must be crafted using iterative computational methods. Examples include multivariate clustering, spatial statistics, network, so graph theoretic analyses, growth curves, spectral analyses, pattern detection, and feature-based classification. Permutation testing and bootstrapping to obtain empirical confidence intervals are different methods with different goals and mechanisms. I will detail their differences towards the end of this chapter. However, they are sufficiently similar that it would behoove you to have gone through section 13.4 before reading this chapter. Section 16.2, Creating an Empirical H0 Distribution. Section 16.2.1, One Randomized Shuffle. Imagine a dataset comprising two groups, X and Y, with sample sizes of n equals 4 and n equals 3 for X and Y. The hypothesis is that mu of X does not equal mu of Y, and therefore the null hypothesis is H0 is mu sub X equals mu sub Y. This paragraph references figure 16.2, which shows an illustration of one random shuffling during permutation testing for the differences between two sample means. Here we have two panels, A and B. Panel A on the left shows real data, and here we see small boxes labeled X1, X2, X3, and X4 corresponding to the 4 data points from dataset X, and small boxes labeled Y1, Y2, and Y3 corresponding to data points for condition Y. The 4 data points for x are above the 3 data points for y. Back to the text. Imagine randomly reassigning each data point to be in each condition. The sample sizes remain the same, but the data points from group X can be labeled as belonging to group Y and vice versa. This is depicted in figure 16.2, panel B. Here we see the same 7 data points that are visually depicted as I described for panel A, but here they are randomly shuffled. So on the top 4, we have in quotes condition X, or data set X, and here we have, instead of X1 through X4, we have X2, Y3, Y1, and X1. And then for data set quote-unquote Y, we have Y2, X3, and X4. In other words, we've shifted or shuffled the X data values with the Y data values. Back to the text. Notice that we haven't changed any of the data values. That is, all 7 data values are preserved in the shuffling, as is the number of data values in each group. What we have randomly shuffled is the assignment of each data value into groups. You might expect that the means of x and y differ, but do you expect the means of quote-unquote x and quote-unquote y to differ? Actually, the means of quote x and quote y might differ simply due to chance. Indeed, with random reassignment, it is possible that most values in quote x are still larger than most values in quote y, especially with small sample sizes. Still, the difference between the means of the shuffled groups is an empirical average that we can expect if H0 were true. Indeed, if H0 is true, then the group label is meaningless and random, so any group differences are purely attributable to chance. You can probably imagine where this is going. Generate many random shufflings, each time recording the difference in means between quote x and quote y. I'll write more later about how many times to randomly shuffle, but for now, let's just say we do it 1,000 times. Section 16.2.2, a distribution of shuffled statistics. Those 1,000 mean differences are samples of a distribution. It is not a distribution of data values, but a distribution of randomly shuffled mean differences. The histogram in figure 16.1 shows an example of what that distribution might look like. Remember, I described figure 16.1 in the beginning of this chapter. The empirical null hypothesis distribution is just a histogram that looks roughly Gaussian. What does that distribution reflect? What we've done is create situations that we could expect to arise if the null hypothesis were true. Indeed, if H0 were true, then the condition labels are arbitrary and meaningless because all data were drawn from the same population. In other words, we've created an empirical distribution of H0 values. To illustrate this concept, I simulated 120 numbers randomly drawn from normal distributions, 50 of which were drawn from normal distributions with mean of 0 and variance of 1, and 70 were drawn from normal distributions with the mean of 0.3 and also a variance of 1. The real data and their empirical means are shown in figure 16.3a. Figure 16.3 shows an illustration of permutation testing for evaluating the differences of means between two samples. There are 3 panels, panels A, B, and C, arranged in a single row. Panel A shows a scatter plot of real data. There are 2 conditions, so the y-axis is labeled data series and has values of 0 or 1. All the values on y equals 0 are gray circles, and all the values on y equals 1 are lighter gray boxes. The data value on the x-axis ranges from around -3 to +2.5, and there are vertical dashed lines indicating the means of the 2 data series. The two data series are largely overlapping, but the mean is shifted to the right for the small circle condition. So data series 0 compared to the mean is slightly to the left for data series 1. Back to the text. I then randomly shuffled the data into two groups with sample sizes corresponding to the sample sizes in the real data. Those shuffled data and their means are shown in figure 16.3b. To be clear, all of the data points in panel B are present in panel A. The difference is that panel A shows the true condition labeling, whereas panel B shows a randomized assignment of data point to group level. So back to the figure, panel B shows shuffled data. Here we see the same overall organization as in panel A, but the data points are randomly swapped between y equals 0 and y equals 1. And we see that in this particular random shuffling, the means are much closer to each other, indicated by the dashed vertical lines. So they're both quite close to 0. Back to the text. Panel B shows one shuffling, which is one iteration in permutation testing. I repeated this random shuffling and recorded the difference in means 1,000 times, and the distribution of those random mean differences is shown in panel C. The dashed vertical line is the empirical sample mean difference, which is visually fairly close to the population mean difference of minus 0.3. So panel C of figure 16.3 shows a histogram of the null hypothesis mean differences between the shuffled data for condition 0 and condition 1. We see a histogram looks roughly Gaussian. It's centered at 0, and there is a vertical dashed line corresponding to the true mean difference at around minus 0.3. Back to the text. The empirical null hypothesis values are not all 0. Indeed, some random shufflings were even more extreme than the empirical value. This is consistent with the analytical H0 approach, which predicts that there is a non-zero probability of observing values more extreme than the observed value. Nonetheless, the empirical null hypothesis distribution is centered around 0, and the bulk of the distribution is clearly to the right of the empirical mean difference. The interpretation is that a mean difference as large as that observed in the unshuffled data is unlikely to have occurred by chance, though it is not impossible considering that a sizable fraction of the randomly shuffled mean differences were left of the observed value. For comparison, I recreated the simulation but specified a population mean difference of 0.1 instead of 0.3. The results are shown in figure 16.4. You can see that the empirical mean difference is close to the center of the H0 distribution. The interpretation of this finding is that a mean difference as extreme or more extreme than the empirical difference is likely to have occurred by chance, given the sample sizes and standard deviations of these data. This paragraph references figure 16.4, which shows another illustration of permutation testing. This figure appears very, very similar. In fact, the layout is identical to figure 16.3. The only difference is that these are different data. So we see the mean difference is smaller. That's apparent in panel A. And in panel C, which shows a histogram of the shuffled distributions, we see that the null hypothesis distribution is still centered at 0. It's still roughly Gaussian shaped. But now the true mean difference is around minus 0.1 instead of minus 0.3. And it's much, much closer to the center of the null hypothesis distribution. Section 16.3, Computing P-values. I hope you have the intuition that the result in figure 16.3 is likely to be statistically significant, while the result in figure 16.4 is unlikely to be significant. Indeed, just like with analytical H0 distributions, statistical significance is based on the empirical test statistic, and in this case, the unshuffled sample mean difference, being far enough away from the H0 distribution. That distance is quantified using a p-value, which is the probability that the empirical effect, or one more extreme, could have been observed by chance if H0 were true. Now, with parametric analyses, the p-value is calculated directly from the distribution because that distribution is a probability function. With permutation testing, however, the distribution is represented as a histogram, not a probability function. There are two ways to compute a p-value from an empirical H0 distribution. One important concept to understand, which I will mention here and you will explore several times in the rest of this chapter, is that because the distribution is built from random shufflings, the distribution and its associated p-value will differ each time you reanalyze the same data. Section 16.3.1, p-value based on normalized distance. If the empirical H0 distribution is roughly Gaussian, you can compute the p-value using a normalized distance to the center of the distribution. Specifically, compute the z-score of your empirical mean relative to the H0 distribution. In the equation below, I'm using delta to indicate the observed mean difference, that is, without random shuffling, H0 to indicate the H0 distribution, and H0 bar, so H0 with a horizontal bar over it, and S sub H0 to indicate its mean and standard deviation. Here we have equation 16.1, which reads Z equals the fraction delta minus H0 bar divided by S sub H0. The preceding paragraph references figure 16.5, which shows computing a statistical z-score using an empirical H0 distribution. Here we see a histogram that looks roughly Gaussian, with the x-axis being labeled parameter value and spanning from -5 to +5. At 0, or roughly 0, we have a vertical dashed arrow indicating H0 bar, so the average of the H0 distribution. And then there is a smaller horizontal bar corresponding to S sub H0, so the standard deviation of that distribution. And then to the right, at somewhere around x equals 4 or so, there is a thick black downward-facing arrow indicating the observed statistic, and the equation that I just read, equation 16.1, is repeated in the figure. The idea of this figure is to illustrate the concept that we are measuring the normalized distance of the observed statistic away from the center of the empirical null hypothesis distribution, and that normalized distance is called Z. Back to the text. You can then interpret that Z value as the number of standard deviations of the observed value away from the center of the H0 distribution. Therefore, you can convert that Z value into a p-value using a standard normal distribution. For example, a Z value of 2.3 would correspond to a two-tailed p-value of around 0.02. For comparison with the next subsection, I will call this p sub z to indicate that the p-value is computed from a z value. Computing and interpreting p sub z is based on the assumption that the z-score is a useful and interpretable metric of the H0 distribution, which is the case if the distribution is roughly Gaussian. Section 16.3.2, p-value based on counts. You can also compute a p-value by counting the number of H0 values that exceed the empirical value and dividing by the total number of permutations. I will call this p sub c, where c is for count, to disambiguate it from p sub z. This paragraph references figure 16.3, which shows a diagram of computing a one-tailed p-value by counting extreme H0 shuffles. Here we see a distribution But this histogram is clearly non-Gaussian. It looks kind of power law distributed. So basically very large values to the left at 0, and then the values fall off precipitously as the x-axis increases up to around 10. There is a vertical black arrow at around 0.5, value of 5, indicating the observed statistic. All of the bars in the histogram to the left of that value are light gray, and all of the bars to the right of that value are drawn in black. And then we see an equation printed in the figure which reads P equals the sum of h naught greater than observed divided by n h naught. Back to the text. To make the test two-tailed, count the number of iterations in which the absolute value of the permuted test statistic exceeded the absolute value of the empirical test statistic. In other words, the total number of h-naught values more extreme than the empirical value regardless of the sign. Depending on the location and shape of the distribution, you might need to mean center. Also, keep in mind that some non-normal distributions are intrinsically one-tailed. For example, the distribution in figure 16.6 might reflect sizes, for example, from a spatial clustering analysis, and therefore only the right tail is sensible to include when computing P sub c. One feature of P sub c is that it is possible to obtain a p-value of exactly 0. This may seem wrong from the perspective of mathematically defined parametric statistics, because p-values are never exactly equal to 0, but instead get increasingly close to 0 as the test statistic gets more extreme. If this bothers you, then think of the p in P sub c as an abbreviation of proportion instead of probability. Section 16.4, Permutation Testing for Means. The illustrations in section 16.2 were not formally t-tests because no t-values were computed. Instead, the test was simply based on the mean differences, which is the numerator of the two-sample t-value. The fact that we did not need to scale the mean difference by these standard deviations highlights an advantage of permutation testing. Standard deviations are built into the null hypothesis distribution, a concept you will explore in exercise 5. Indeed, scaling the data by any arbitrary number except 0 wouldn't affect the statistical result because the h-naught distribution will be scaled by that same arbitrary number. For this reason, a permutation-based test of sample mean differences serves the same purpose as the t-test, and is therefore colloquially called a permutation t-test. But the test is not based on t-values. Indeed, it is not desirable to compute a permutation-based t-test by scaling the observed and shuffled mean differences by their standard errors. This is because each random shuffle will have a different standard deviation, which means that each element of the h-naught distribution will have its own scaling. Section 16.4.1, Permutation Testing for a One-Sample Mean. The examples presented so far involved comparing means between two samples. What do you do if you have only one sample, but cannot perform a parametric one-sample t-test? There are no groups to randomly swap. Let's think back to the null hypothesis of the one-sample t-test. That is, h-naught is mu equals h-naught. If the null hypothesis were true, you would expect roughly half of the mass of the data to be below h-naught and half of the mass of the data to be above it. Conversely, strong evidence against the null hypothesis would imply that the bulk of the data is on one side of the h-naught value. This insight leads to the mechanism of permutation testing for the mean of one sample, and for now, assume h-naught equals 0. So, swap the sign of a random number of data values and compute the sign-shuffled sample mean. If the sample average is the same before versus after randomly swapping signs, then the data have roughly equal mass above and below the H0 value. Imagine, for example, testing all positive value data against H0 equals 0. Randomly swapping signs would lead to an H0 means distribution centered on 0, with much of its mass to the left of the unshuffled data mean. If the H0 value is not 0, then you first subtract that value from the data to force H0 equals 0. In other words, you shift the data such that the null hypothesis is x minus H0 bar, so the mean of the data shifted by the H0 value, equals 0. In practice, it's useful to create a copy of the data, so you have data x and data x tilde equals x minus H0 to use for statistics. I've run a simulation to illustrate the procedure. I generated 87 numbers randomly drawn from a gamma distribution and tested against the null hypothesis that the average of this sample distribution is 1. This paragraph references figure 16.7, which shows an illustration of permutation testing for the mean of one sample. Here we have two panels. The panel A on the left shows a histogram of data, so clearly non-normally distributed data. The bulk of the distribution is on the left of the distribution, with the values on the x-axis ranging from 0 to a little bit above 4. The observed mean is indicated as a gray dotted line at a little bit above 1, it's around 1.1, and the H0 value is indicated with a thicker black dashed line at x equals 1. Back to the text. The distribution is clearly non-normal, so one might question whether the mean is an appropriate sample characteristic to consider. On the other hand, permutation testing does not rely on assumptions such as normality, so the appropriateness of the mean of the sample may be an issue of interpretation, but it is not an issue of statistical validity. Because the H0 value is not 0, I created a copy of the data that were mean-centered on the null hypothesis value, and then I reshifted them for visualization. Permutation testing involved computing the mean of the H0 shifted data multiplied by a random vector of +1s and -1s. Figure 16.7b shows the histogram of the distribution of permuted means. The observed mean was towards the tail of the distribution, but the two-tailed p sub c was 0.187, indicating that we cannot reject the null hypothesis. In other words, these data could have been drawn from a population with mu equals 1. This paragraph references figure 16.7 panel B. Panel B shows a histogram of the shuffled means shifted so that the center of the distribution is at x equals 1 approximately, and we see a vertical dotted line for the observed mean at around a value of 1.1, maybe it's a little bit above 1.1. Back to the text. I then reran the permutation testing multiple times without recreating the data. The p-values changed each time I reran it, but they were always greater than 0.05, indicating that I would not have drawn a different conclusion about the data. That is not guaranteed to happen. It is possible for some random permutes on the same data to have p greater than 0.05, while others have p less than 0.05. I will discuss this issue in a later section, and you'll see in exercise 2 an example of how repeatedly testing the same statistic can lead to different conclusions. Section 16.4.2, Permutation Testing for a Paired Sample Mean. Recall from Chapter 11 that a paired sample t-test is implemented by subtracting the paired data values and then implementing a one-sample t-test. The concept is the same in permutation testing. Subtract the pairs and test H0 equals 0. Another way to think about why this is the right procedure is that for paired conditions A and B, the null hypothesis predicts that the mean of A equals the mean of B, which means that A minus B should equal B minus A. Thus, randomly shuffling to simulate the null hypothesis involves computing A minus B and randomly multiplying that difference by +1 or -1, because minus the quantity A minus B equals B minus A. Section 16.5, Permutation Testing for Correlation. Before reading further or looking at the figure for this section, I would like you to think about how to implement permutation testing to evaluate the statistical significance of a correlation coefficient. So, what would you permute, and how would you derive a p-value? Well, I hope you took the time to consider this question before listening further. The answer is that you permute the mapping between the data values. You do not need to swap data observations between the two variables. In fact, this is not desirable if the variables have different numerical scales. Instead, you randomly shuffle the ordinal positions of the data values within one variable. It is not necessary to shuffle both variables as long as the pairing is randomized. This is illustrated in figure 16.8. Notice that the X data stay in the first column and the Y data stay in the second column, while the row indices of Y are randomized. This paragraph references figure 16.8, which shows an illustration, a diagram of one random shuffling during permutation testing of a correlation coefficient. We have two panels, panel A on the left and panel B to its right. Panel A is titled Real Data, and we see a 4x2 matrix of little boxes that represent a small data set. So the left column reads x1, x2, x3, x4, and the right column reads y1, y2, y3, y4. Then we have panel B, which has the same overall organization. In fact, the left column is identical, x1, x2, x3, x4. The second column for the shuffled dataset is listed y2, y4, y3, and y1. So the idea is that the data values are preserved as well as their column assignment. What is shuffled or randomized within this one random shuffling in permutation testing is the mapping between the paired values in X and their corresponding values in Y. Back to the text. From here, permutation testing for the statistical significance of a correlation coefficient proceeds in the same way as described in earlier sections. Repeat the random shuffling many times, record the shuffled correlation coefficient, and then compute a p-value as the observed correlation coefficient relative to the distribution of H0 coefficients. You will have the opportunity to implement this in exercises 6 and 7. Section 16.6, How many permutes? Why did I use 1,000 random permutes for all of the examples in this chapter so far? Obviously, one single random permutation is insufficient, but is there some deep mathematical statistical theory that mandates using 1,000 shuffles? No, there is no theory that tells us how many permutations to use. It is important to have enough permuted values to estimate an H0 distribution, but how many are enough? Well, that depends in part on the data. Clean data without outliers will have cleaner empirical null hypothesis distributions, which means that fewer iterations are necessary. On the other hand, there is no theoretical downside to increasing the number of iterations. Well, that's not entirely true. The theoretical upper limit on the number of permutations corresponds to the total number of ways to permute the data. For example, with a mean of one sample in which the permutation test is carried out by multiplying a random subset of numbers by -1, the total number of unique permutations is 2 to the n, which is a really large number. For example, a sample size of n equals 40 has 1,000 trillion ways of being permuted. And for reference, there's an estimated 200 billion galaxies in the known universe. And n equals 40 is not a terribly large sample size. But the practical limitation of a large number of shuffles is the computation time. If you're performing only one t-test, then running a huge number of permutations is not a big deal. But for large data sets in which thousands of tests are being performed, shuffling each sample millions of times may be prohibitively computationally expensive. Figure 16.9 shows a simulation in which I computed characteristics of the H0 distribution using a range of iterations from the test shown in figure 16.7. The three characteristics are the p-value of the sample, the mean of the H0 distribution, and the width of the H0 distribution, quantified as the IQR, interquartile range. The results were mean-centered so that they could be visualized on the same plot. This paragraph references figure 16.9, which shows characteristics of an empirical null hypothesis distribution, mean-centered for visibility, as a function of the number of iterations. Now what we see is a scatter plot with three different colors corresponding to different features of the H0 distribution. We have the p-value in blue, the H0 mean, so the mean of the distribution, in orange, and in green we have the width of the distribution. Okay, on the x-axis we have the number of iterations ranging from 1 to 10,000. And then on the y-axis, we have the mean-centered distribution characteristic value. Okay, and basically what we see is that there is some variability, so there's some differences for a different number of iterations going up to around, I don't know, maybe 1,500 or 2,000 or so. And after that, it's pretty stable in the sense that the variability of the p-value, for example, isn't really decreasing noticeably as a function of increasing iterations. Now, this result is based on one data sample, but the pattern is consistent with myriad observations in myriad data sets. Back to the text. The key take-home message from this figure is that the values don't change much, except when using a small number of iterations. Of course, this claim is based on one example from one simulated dataset, but it is consistent with myriad evaluations that I and many other people have done using real and simulated data with various characteristics and from various sources. The consensus is that, although results from permutation testing vary each time it is rerun, the number of iterations doesn't make a huge difference as long as you have at least several hundred iterations. The law of large numbers comes into play here as well. As the number of permutations increases, the estimate of the shape of the null hypothesis distribution becomes increasingly accurate. The conclusion of this section is that having more iterations in permutation testing is good, but only up to a point. Section 16.7, What to permute. The general idea of permutation testing is simple. Repeatedly shuffle the data to create an empirical null hypothesis distribution. But what do you shuffle? You've already seen that there are different ways of shuffling the data depending on the nature of the data and the desired statistic. For example, multiplying randomly by -1 versus changing the pair of data values. Herein lies the tricky part of permutation testing. There are often several ways of manipulating the data, but not all manipulations make sense. There are two general principles to keep in mind. General principle 1. Change only what the H0 predicts. For example, a correlation analysis is about the relationship between variables, not about the mean of each variable. Therefore, it makes sense to shuffle the pairing of the values but it does not make sense to shuffle the sign of the values within the variables. Likewise, the H0 for a test of the median of one sample predicts that the same number of data values is smaller versus larger than the median, but the H0 has nothing to say about the ordinal position of the data values within the variable. General Principle 2. Preserve as much of the data as possible. Try to change the data as little as possible. The more you change the data, the higher the risk that the H0 distribution will not reflect the real data. A trivial example. If you square the data during shuffling, then the H0 distribution will contain values much larger than the real data. Section 16.7.1 Permutation World. One of the advantages of permutation testing is that it is a general framework for performing inferential statistics when assumptions are violated or when the analytical H0 probability function is unknown. This means you can adapt and apply permutation testing to a wide variety of applications. Permutation testing is used in time series analysis, spectral decomposition, genomics, machine learning, econometrics, and myriad other applications. As you venture out into the world of applied statistics and machine learning, you will discover and perhaps develop many specific instances of permutation testing. However, they are all built on the same principles introduced in this chapter. You can also incorporate the principles outlined in this chapter to obtain statistical significances for regression and ANOVA models. Section 16.8 Permutation Testing versus Bootstrapping. Permutation testing and bootstrapping for empirical confidence intervals are conceptually related in that they involve shuffling the sample data to estimate a statistical quantity. They are also both central techniques in computational statistics, but their mechanisms and applications are different. People sometimes confuse the two, so I hope this text below helps you appreciate how they differ and how they can be combined. Mechanisms. Permutation testing is done by shuffling the data labels for a two-sample test, the ordinal positions for correlation, or signs for a one-sample test. Data are not repeated or omitted. In contrast, bootstrapping is done by resampling the data without altering the labels, positions, or values. Data may be resampled repeatedly or may be omitted from the resample. Goals. The goal of permutation testing is to obtain a p-value to evaluate statistical significance. As you know from several previous chapters, statistical significance is not the same as effect size. In contrast, the goal of bootstrapping is to obtain interval bounds on a parameter estimate. Although confidence intervals can be used for statistical significance, the primary goal is to produce a range of plausible values of a population parameter. You can see that permutation testing and bootstrapping are complementary, and you can use both in your analyses. Section 16.9 Why not always use permutation testing? You might be thinking that permutation testing is the best framework for inferential statistics. You don't need to worry about assumptions or outliers or other unusual data features to deal with. It can be adapted to myriad influential statistics, so why would anyone prefer traditional parametric statistics? There are several reasons why traditional parametric statistics have remained nearly ubiquitous in quantitative sciences. Reason 1. Parametric statistics are deterministic. Each time you run the same analysis on the same data, you get exactly the same results. And anyone else with your data will get exactly the same results from the exact same analysis. This is useful because reproducibility is important for scientific progress. In contrast, permutation-based statistics will give different results each time you rerun the analysis on the same data. Hopefully, the conclusion about the data will remain the same, even if the numerical results change, but there will be situations in which the same analysis on the same data sometimes leads to a conclusion of significant, while other times being non-significant. See exercise 2. This volatility justifiably makes some people uncomfortable. Reason 2. Parametric statistics have a strong mathematical foundation. Many parametric statistical approaches can be mathematically proven to be optimal, whereas some shuffling-based methods are sensible algorithms. That is troubling to many mathematical statisticians, although it may not be bothersome to applied data scientists. Reason 3. Historical precedents. Permutation-based statistics depend on modern computing power. Random data shufflings were simply infeasible a century ago. Imagine doing 1,000 iterations of permutation testing on a dataset of n equals 20 by hand. It is possible that permutation-based statistics would be more common if statistics were developed in the age of computers. Indeed, modern statistical and machine learning analyses increasingly rely on shuffling methods like permutation testing and bootstrapping. Reason 4. This is related to the previous point. People do things in a certain way because that's how they were taught, and therefore that's what they teach their peers and students. People continue to rely on parametric statistics because most other people rely on parametric statistics. I don't write that with any negative judgment. We should not abandon time-proven, established methods simply because newer methods exist. But we should also resist the temptation to continue the old ways solely because that's what we were taught by even older stats professors. To be honest, I'm not sure what to conclude from this discussion. I admit that in my own published research, I have occasionally used parametric statistics simply because I was concerned that permutation-based statistics would raise questions from reviewers and readers. The thing is that when you have clean data with either a strong effect or no effect, the conclusions about the data are the same regardless of the statistical approach. You'll see several examples of this in the exercises. My advice about when to use permutation-based versus parametric statistics is similar to my advice about many other choices in data analysis. Try to do what is commonly done in your field and use alternative or less common methods when they are justified. All that said, computational statistical methods, including permutation testing and bootstrapping, have become more popular and widespread due to increasing computational power and efficient algorithms. Section 16.10, Exercises. As you know, I recommend you check out my YouTube channel for video overviews of the exercises and their solutions. End of Chapter 16.